Here we're going to describe and calculate the derivative of inverse trig functions. If inverse trig functions were something that you totally don't remember at all, it might be helpful to go back and take a look at lesson 5 from the summer videos. I will do like a very quick kind of sort of review of inverse sine, but it would be helpful maybe to take a look back at your notes and refresh your memory. So we'll start with inverse sine. We'll do this one in depth, and then we'll just kind of present the derivative rules for the other inverse trig functions. So let's remember inverse sine. So if I have the function y equals inverse sine of x, and it's important to remember what this means. If we take the inverse sine of something, what are we getting back out? Well, what we're getting back out, and I'm going to put this in parentheses because this isn't a mathematical equal sign. What essentially we're finding is the angle whose sine is x. It's helpful to remember that inverse means that you're switching the role of the input and the output. So if you just think about sine of x for a second, just the normal function, not the inverse of sine, what you're doing is you're inputting an angle. So you might input pi over 4. And finding the sine of pi over 4 means you're finding the y-coordinate where the terminal side of the angle pi over 4 intersects the unit circle. And then what you'll get out is that y-coordinate, right? And root 2 over 2 in the case of pi over 4. Now when we switch the role of the input and the output will now be the angle, and the input will actually be the y-coordinate value. So for inverse sine, I'm inputting this particular y-coordinate value and asking where or what angle has a sine that has that particular value. In other words, I'm looking for the angle whose sine is x. So we can draw a little picture here to help us understand this. So first consider the unit circle, right? And for the inverse sine, the input are going to be all the possible values that sine could have, all the possible y-coordinates that you could have on your unit circle. And you realize that you don't actually have to look at the whole unit circle. All of the possible y-coordinates that you could have show up if you just go from negative pi over 2 around to positive pi over 2. Here you'll get all the negative y-coordinates, here you'll get all the positive y-coordinates. So the inverse sine, we only need to define for inputs between negative 1 and positive 1, right? Because when we're asking the angle whose sine is this value, all the possible values that sine could have are from negative 1 to positive 1. So that's why we only need to graph it from negative 1 to positive 1. Now I need to think about, okay, what are the actual values of inverse sine going to be? So if you think about inputting negative 1, you'd be asking yourself, the angle whose sine is negative 1. Well, what's the angle whose sine is negative 1? That's going to be negative pi over 2, right? Rotating negative pi over 2. So it'd be down here. And you could then you could go a couple more points over here. You could say, okay, what's the angle whose sine is 0? Well, that's the angle 0, right? And then you could go over here, you could say, what's the angle whose sine is 1? Well, that's pi over 2. Okay. And you can go ahead and connect like that. And what you can sort of see are a couple things. The first is, as I get closer to here, I can notice that the function is getting pretty close to vertical. In fact, it will have a vertical tangent here. And so we can actually only get the derivative for points in between negative 1 and 1. And we'll talk about that when we clearly state the definition. So if we're just thinking about when we find the derivative of y, or y prime, we're finding the slope of this line here. This is the graph of inverse sine of x. So that's just always important to remember. We're still just finding the slope at any instant along this curve here. So you can imagine when I plug in values between 0 and negative 1, I should have a positive slope, in other words, the derivative should be positive, and when I plug in values to the right, between 0 and positive 1, I should still be getting positive values, right? So the derivative of inverse sine should always be positive, right? The slope is always positive. And so that's an important thing to remember when we go through and actually find the derivative. All right, one more thing that's going to help us when we take the derivative here is to actually draw a quick little diagram. And remember, I don't need these quadrants here. To draw a quick little diagram of what actually inverse sine of x being equal to y looks like in the unit circle. So I'm just going to take a generic angle out of my unit circle, and I'm going to draw it over here. Now remember, I'm keeping this as general, but this point here is always going to be the origin. But this should work for this is going to represent any possible angle that I rotate between negative pi over 2 and positive pi over 2. In other words, it will be for any input between negative 1 and positive 1. So for this particular situation here, y is representing the angle whose sine is x. So the angle here is y. Now x is actually representing the y-coordinate. So we can drop this perpendicular down. That distance will represent the y-coordinate, and that's the input. Right? We're inputting the y-coordinate value or the sine value, and what we're hoping to get out is the angle whose sine is that particular value. So that angle is represented as y. X represents that input or the y-coordinate or y distance from the x-axis, and the radius, of course, of the circle is 1, and so this, what you can think of as the hypotenuse of this right triangle here, is 1. Now there's one more thing that we can define, and that's the other leg of this right triangle. I'll draw it in red here. What is that? Well, this is just the x distance for this particular angle for the point that intersects the unit circle. And so this is actually the cosine of this. So let's write that down here. That'll end up being very useful. And we can say a little more, because using the Pythagorean theorem, we can represent this in terms of these other pieces here. Notice up here I don't have, cosine hanging out anywhere. So we'd like to represent it in terms of x and 1. The Pythagorean theorem says that this side length squared plus this side length squared has to equal the hypotenuse squared, in this case 1. And so writing this out, we have cosine squared plus x squared equals 1. Well, that means that cosine of y squared will equal 1 minus x squared. And so if I take the square root of both sides, I'm left with cosine of y being equal to the square root of 1 minus x squared. So what we can say is that this side length here is the cosine of y, or in other words, square root of 1 minus x squared, just by the Pythagorean theorem. That would be helpful. Okay, so now that we have clearly identified what each of the different pieces in our function is in relation to the graph of this actual function, that helps us understand that we're finding the derivative or the slope of this curve at any point, and also where these actual inputs and outputs are relative to the unit circle, since this is a trig, an inverse trig function. And now we're ready to take the derivative. So to take the derivative, we're actually going to do something kind of creative that's called implicit differentiation. And we're going to learn this later on. So I'm not going to define it for you now. I'm just going to kind of talk you through the common sense of how we make this happen. The first thing we want to do is try and write this equation with something that we've actually taken the derivative of before. And we've taken the derivative of sine before, which will be easy because we can rewrite this in terms of sine. This is the inverse relationship. So if we think about the original relationship that this came from, what we're saying is the sine of y will be x. And this should make sense because this is saying the angle whose sine is x, meaning if I took the sine of this angle, I'd get x. Nothing too crazy. So now I can take the derivative of both sides. Because if I take the derivative of both sides, I'll be taking the derivative of sine and the derivative of x. And I've done both more or less before. So the derivative with respect to x, right? Because remember, I want to find the derivative of y. So the derivative with respect to x of this times the derivative with respect to x of this. Okay, well, let's think about the right side first. What's the derivative of x with respect to x? That's just 1. Well, what about this over here? Notice that I'm taking the sine of something. I'm taking the sine of y. Well, y itself, remember, we defined it originally as the function of x. In fact, that's the thing we're trying to find the derivative of eventually. So when I'm trying to take the derivative of this, I have to use the chain rule because this is the sine of some function of x. So I'll use the chain rule here. I'll take the derivative of sine with respect to y. So that will just be the cosine of y. And then I have to take the derivative of the inside function, which is the derivative of y with respect to x. This is actually great news, because what we're trying to do is actually take the derivative of y with respect to x, and this is the same y. So if I can isolate the derivative of y with respect to x, then I found the derivative I'm looking for. Well, if I want to solve for this, I've got to divide by the cosine of y on both sides. So I will end up with dy dx is equal to 1 over, or divided by, the cosine of y. Now, the one thing that we would have to make sure we're not doing is dividing by 0, but you'll remember that we talked about how you can't actually take the derivative at these endpoints because they're going to be vertical tangents. And so the only place that cosine of y would be 0 is if our angle y was pi over 2 or negative pi over 2. And because we're not letting the input x be 1 or negative 1, we're never going to have a situation where the cosine of y is the cosine of negative pi over 2 or positive pi over 2. And we'll actually see this pop up again when we look at the answer in its final form. Notice now that we have the derivative of y with respect to x, and it's determined by a function of y. And that's no good, because we want to find the derivative of y as x is changing, and so we'd like to be actually able to plug in an x value. But we've already kind of helped ourselves out in this regard because we wrote the cosine of y in terms of x as the square root of 1 minus x squared. That is the cosine of this angle y. So the derivative of y with respect to x is equal to 1 over the square root of 1 minus x squared. And so there's one last thing that we need to make sure, and that's what we just talked about previously, which is the denominator can't be equal to 0. Well, this will be equal to 0 when x is either 1 or negative 1, right? We just talked about how we wouldn't let the x value be negative 1 or positive 1, because at that point the tangent line would be vertical, meaning the slope would be undefined. And since our derivative is just the slope, it would be undefined, as we see here. So we have to say this is for x less than 1 greater than negative 1. And this is the derivative of the inverse sine of x. So what you can think about is if I had inverse sine of some function u, which also has a derivative, then the derivative with respect to x of inverse sine of some function u, which is also a differentiable function, would be, well, remember, I take the derivative of the outside, which is the derivative of inverse sine, which would be this with respect to u, times the derivative of u. So it would be 1 over the square root of 1 minus u squared times the derivative of u with respect to x. And again, this is only for when u is less than 1 and greater than -1, right? And one way that I can say that, instead of using two inequalities as I did previously, I can just say that the absolute value of u must be less than 1. And that means, of course, that u can't be equal to -1 either, because the absolute value of -1 is 1. And so this is the definition of the derivative for the inverse sine. So let's go ahead and take a look at the other inverse trig function rules, and then we can apply them. All right, so here are the derivative rules for inverse trig functions. The first one we just talked about, the derivative of inverse sine of u, and u here is a differentiable function of x, as we've seen all throughout the course. The derivative will be taken using the chain rule, so the derivative of the outside, which is the inverse sine, which we just found, is 1 over the square root of 1 minus u squared, and then times the derivative of the inside function, which is du dx. And this is, of course, when the absolute value of u is less than 1, so that we don't have an undefined derivative. Sometimes you'll see people write this du dx just in the numerator of this expression, because when you multiply, that's where it ends up. And sometimes they'll write it as u prime. Let me show you. They'll write it as u prime. So instead of 1 here, they'll just write u prime. And I don't like to do that because I think it gets away from the understanding piece, which is I have the chain rule being implemented here. So I don't like to write that, but you could. So now let's think about inverse sine of u, inverse cosine of u. And with inverse cosine of u, I'm actually going to pull up a graph of inverse sine and inverse cosine to see if we can tell the relationship. All right, so here I've pulled up a graph of both inverse sine and cosine, and you don't need to copy this down. You already have the graph of inverse cosine. We just graphed that, right? The angle whose the angle whose sine is -1, that angle would be -pi over 2. The angle whose sine is +1, that'd be +pi over 2. Now for cosine, if you think about it, cosine can go between -1 and 1 as well. What's the angle whose cosine is -1? Well, if you think about your unit circle, you go halfway around it, pi radians, that's where cosine is -1. Where is cosine 1? Well, the angle whose cosine is 1 is the angle 0. So we can see this function here. But we want to compare the derivatives, so we want to compare the slopes of the graph. So if you take a look at the slope of sine, how is it in relation to the slope of cosine? Well, the first thing you notice is the slope of sine is positive, and the slope of cosine is negative. But other than that, they look pretty darn similar. If you took a look at the slope right here and the slope right here, gosh, they look really similar, except one is just decreasing and one is increasing. Same can be said right here and right here. In fact, it's pretty obvious if you look at it and study it a little more closely that the slope of inverse cosine is just the opposite of the slope of sine. In other words, I just multiply the slope of sine, or the derivative of sine, by a negative, and I get the slope of cosine. And if you want to do a little more investigation about algebraically why this is the case, what you want to look for is the relationship between inverse sine and inverse cosine. How could you write inverse cosine in terms of inverse sine? But this gives us enough intuition to take a look at the rule and understand why it makes sense. So here's the rule for inverse cosine. The derivative of inverse cosine of u is -1 over square root of 1 minus u squared times the derivative of u with respect to x. Notice it is the exact same as, is the exact opposite of inverse sine, the derivative of inverse sine. That's because their slopes are opposites. And again, the absolute value of u must be less than 1. All right, let's take a look at tangent now. So if I take a look at tangent, and don't worry about cotangent for now, just take a look at tangent. So the derivative with respect to x of inverse tangent of u is 1 over 1 plus u squared times the derivative of u with respect to x. Here, notice there's no constraint on u. Why is that? Well, the tangent, remember, that's just the slope of the terminal side, and we can have any possible slope you could imagine, from perfectly horizontal to perfectly vertical. So no matter what u is, I'll be okay. When I square it, it'll never be negative, so I'll never have 0 down here. And you can think about how you'd prove this, right? And we can do so in class if you want. Let's take a look at inverse secant and inverse cosecant. Before I get started, let's just remind ourselves the reciprocal of sine, in other words, 1 over sine of x, is cosecant of x. The reciprocal of cosine, 1 over cosine of x, is secant of x. So when we're not talking about the inverses, in particular the derivatives of the inverses, because we're going to notice a relationship in a second, but when we're just dealing with sine, cosine, secant, and cosecant, we're thinking about the relationship where the reciprocal of sine of x is cosecant of x. So cosecant is 1 over sine, and secant is 1 over cosine. So keep that in mind, and if you need to write it down again, go ahead, because we're going to notice a relationship that runs a little counterintuitive to that in a second. The derivative of inverse secant of u is 1 over absolute value of u times the square root of u squared minus 1 times the derivative of the inside function, or derivative of u with respect to x. Notice again that the absolute value of u is constrained, has to be greater than 1. If it's less than 1, I'll get a negative in here, and that will be an imaginary slope, and I don't want that. The derivative of inverse cosecant of u is just the opposite, or negative 1 times whatever the derivative of secant, inverse secant of u was. So I get negative 1 over absolute value of u times the square root of u squared minus 1 times the derivative of u with respect to x. Again, the absolute value of u is constrained to being greater than 1 for the same reason. But notice, just as how inverse sine of u and inverse cosine of u were just opposites of one another, inverse secant of u and inverse cosecant of u, their derivatives are also the opposite of one another. The way I remember it is that the inverse sine starts with s, inverse secant also starts with s, and so both of their derivatives do not have a negative. Inverse cosine and inverse cosecant both start with c, so they both have a negative. Remember, these are not, the reciprocal of sine is not secant. The reciprocal of sine of x is cosecant. But this is an easy way to remember these sort of confusing derivative rules. Make sure you write these down. One last relationship to look at is the relationship between inverse tangent and inverse cotangent. Notice that inverse cotangent's derivative is just negative 1, or the opposite of inverse tangent. So the derivative of inverse cotangent of u is negative 1 over 1 plus u squared times the derivative of u with respect to x. All right, now that you've got all that written down, hopefully copied also into your terms and definitions packet, it's time to go ahead and apply these and make sure that we can utilize them to solve some problems and find some derivatives. All right, so let's try this one out. Notice here that I've written inverse cosine in its alternate form, which is arc cosine. And so that's one thing you might want to add if you've forgotten. I can alternatively write them as arc sine, arc cosine, arc tangent, arc secant, arc cosecant, arc cotangent. That means the same thing as inverse cosine of e to the 4x. So what I like to do here is I like to actually write out my derivative rule. That helps me remember it each time. So I'll go ahead and write that out. You should try that. Try to write it out from memory. You might totally get it wrong. That's okay. Just try it and then go back and rewrite it again. All right, so I have it written out here, and in order to follow this, what I would like to do is actually name what u is in my derivative, so that way I can literally just rewrite this with what u and du are. So in this case, my u, my function of x, is e to the 4x, and if I took the derivative of that, the derivative of u with respect to x is equal to, and the derivative of e to the u is just e to the u, e to the 4x, times the derivative of u, which is just 4. So now I can just rewrite my derivative following the rule and plug in the value that I have for u, and the value that I found for the derivative of u, for the derivative of u. So what I'm going to have is negative 1 over the square root of 1 minus e to the 4x e to the 4x squared, all inside the square root, times the derivative of u with respect to x, which is 4e to the 4x. I can simplify a little bit, multiply in on the numerator. It gives me negative 4e to the 4x. And in the denominator, I have the square root of 1 minus, and when I square something, I'm multiplying by itself twice. So I'll have e to the 4x times e to the 4x. It means I add the exponents, so I'll have e to the 4x plus 4x, or 8x. Now here's my derivative, but notice the constraint that I had, which is that the absolute value of u has to be less than 1. Because if it were greater than 1, I'd be subtracting away something from 1 that is bigger than 1. In other words, I'd get an imaginary number down here, and that's not going to work. Well, here, u is e to the 4x. So the absolute value of e to the 4x has to be less than 1. And that's important, because if that's not the case, then I'll be in a little bit of trouble. And what I encourage you to do is actually think about what that means about what x has to be. Take a look at the graph of e to the 4x and see what would x have to be to keep it less than, keep the absolute value of it less than 1. I'll let you think about that there. This will make more sense when we're doing this for real-world problems, because you'll have to put some constraints on the input where you can actually find the slope. There'll be places where you can't actually find the slope. So this is the derivative of the inverse cosine of e to the 4x. A couple things to take away here. The first was to write out your derivative rule. Do that for every one that we practice on. That way you'll remember them. That'll help you. And then write out what your u is and take the derivative of it. That way when you go to apply your rule, you literally are just looking for u and du dx, and you can plug in your values there. Okay? Right? You're still using the chain rule. So you're taking the derivative of the outside with respect to whatever the u value is, whatever that function is, and then the derivative of u multiplied on the outside. All right? Those are a couple of tips. I'm going to give you a couple to try that we can present in class. All right, go ahead and complete these. Make sure that you're writing down the rule that you're using to help you remember them, and also to delineate what the u function would be in this case, so that you can just find the derivative of that function u and then use that rule that you've written down.